Welcome to our channel, where we explore the wonders of the universe and the groundbreaking science that helps us understand it. Today, we're embarking on a journey that could change the way we see our place in the cosmos. We're delving into the search for Earth-like exoplanets, those distant worlds that might, just might, harbor life. Central to this quest is the upcoming Habitable Worlds Observatory, or HWO, a mission that could redefine our understanding of planetary systems and the potential for life beyond Earth. Let's start by understanding the stakes. Earth-like exoplanets, also known as Exo-Earths, are planets outside our solar system that resemble Earth in key ways. They're rocky, roughly Earth-sized, and orbit within their star's habitable zone, the region where liquid water could exist. Water is essential for life as we know it, so finding planets where it could be present is a big deal. But just how common are these planets? Are we alone in the universe, or is our galaxy teeming with habitable worlds? These questions have driven astronomers for decades, and the answers are slowly coming into focus. We've already confirmed the existence of over 5,700 exoplanets, thanks to missions like Kepler and TESS. However, finding Earth-like planets is particularly challenging. They're small, faint, and often lost in the glare of their parent stars. That's where the HWO comes in, designed specifically to find and study these elusive worlds. The Habitable Worlds Observatory, set to launch in the 2040s, is the culmination of years of planning and technological development. It was recommended by the Decadal Survey on Astronomy and Astrophysics 2020, a key report that sets the priorities for space research in the United States. The HWO is not just another space telescope. It's the first mission explicitly designed to search for signs of life on planets outside our solar system. This mission could help answer one of humanity's most profound questions. Are we alone in the universe? HWO will use a technique known as direct imaging to find exo-Earths. Unlike other methods, which infer the presence of planets by their effects on their parent stars, direct imaging captures actual pictures of planets. This allows scientists to study these planets in unprecedented detail, from their atmospheric composition to potential surface features. Imagine being able to see a planet orbiting a star tens of light years away, analyzing its atmosphere for signs of life, or even detecting weather patterns. That's the power of direct imaging, and it's what makes the HWO so exciting. Direct imaging is a relatively new method in the field of exoplanet discovery. Most of the exoplanets we know of today were found using methods like the transit method or radial velocity. The transit method detects planets by measuring the tiny dip in a star's brightness as a planet passes in front of it. Radial velocity measures the slight wobble in a star's motion caused by the gravitational pull of orbiting planets. While these methods have been incredibly successful, they have limitations, especially when it comes to finding Earth-sized planets in the habitable zone. Direct imaging, on the other hand, allows scientists to isolate the light from a planet and analyze it separately from the star's light. This is done using a device called a coronagraph, which blocks out the star's light, making it possible to see the much fainter light reflected by the planet. This method is still in its infancy, with only a handful of planets discovered this way, but the HWO aims to change that. The mission is designed to detect and study Earth-like planets around the nearest and brightest stars, providing us with the most detailed look yet at potential homes for life outside our solar system. Choosing the right targets is crucial for the success of the HWO mission. Not all stars are good candidates for hosting habitable planets. For example, stars that are too young might not have stable planetary systems, while those that are too old might have lost their habitable zones as their luminosity changed over time. The study led by Dr. Stephen Kane at UC Riverside has been pivotal in refining the list of potential targets for HWO. Out of 164 stars initially considered, Dr. Kane's team found that 30 host 70 known planets. However, not all these systems are ideal for finding Earth-like planets. The study identified 11 systems where the habitable zone is disrupted by the presence of giant planets. These massive planets can gravitationally destabilize the orbits of smaller, potentially habitable planets, making it unlikely that Earth-like conditions could persist. One such system is 55 Cancri, located 41 light-years away. It has 5 known planets, one of which might pass through the habitable zone. Another intriguing system is HD 219134, just 21 light-years away, which has 6 planets, including one that might be in the habitable zone. These systems represent the kind of targets HWO will focus on: nearby, relatively bright stars with the potential to host Earth-like worlds. The process of identifying and studying exoplanets is complex, involving various detection methods. As we've mentioned, direct imaging is at the forefront of the HWO mission, but it's not the only tool in the astronomer's arsenal. The transit method, radial velocity, and even gravitational microlensing, where a star's gravity acts as a lens to magnify the light of a more distant star, are all part of the broader search for exoplanets. Each method has its strengths and weaknesses. The transit method, for instance, is excellent for finding planets that orbit close to their stars, but it's less effective for planets farther out. Radial velocity can detect planets based on their mass, but it's challenging to use for small, Earth-sized planets. Direct imaging, while incredibly powerful, is still limited by current technology. It's most effective for finding planets around nearby stars, where the contrast between the star's light and the planet's reflected light is less overwhelming. But the HWO is expected to push the boundaries of what's possible with direct imaging. Equipped with advanced coronagraphs and possibly even a starshade, a spacecraft that flies in formation with the telescope to block the star's light, the HWO will be able to image planets that were previously too faint to detect. This could lead to the discovery of dozens, if not hundreds, of new Exo-Earths. The results from Dr. Kane's study have already had a significant impact on the planning of the HWO mission. By identifying which stars are the least likely to host habitable planets, the study allows scientists to focus on the most promising targets. This kind of efficiency is crucial for a mission like HWO, which will have limited time and resources to conduct its search. The study also highlights the importance of understanding the dynamics of planetary systems. For instance, giant planets like Jupiter can have a profound impact on the stability of a system's habitable zone. In some cases, these giant planets might protect smaller, Earth-like planets by deflecting comets and asteroids. In other cases, they might destabilize orbits, making it impossible for a habitable planet to exist. Understanding these dynamics is key to selecting the best targets for HWO and maximizing the mission's chances of success. As we look to the future, the Habitable Worlds Observatory represents the next step in our search for life beyond Earth. But it's not the only mission on the horizon. The James Webb Space Telescope, JWST, already in operation, is expected to complement HWO by studying the atmospheres of exoplanets found by other missions. The upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will also contribute to our understanding of exoplanets through its microlensing survey, which could discover thousands of new worlds. Together, these missions will provide a comprehensive picture of the diversity of planetary systems in our galaxy. They will help us understand how common Earth-like planets are, what their atmospheres are made of, and whether they could support life. The HWO, in particular, will play a crucial role in this effort by providing the detailed, high-resolution images needed to study these planets up close. So, why does all this matter? The search for Earth-like exoplanets is more than just a scientific quest. It's a search for our place in the universe. Finding another Earth, or even a planet with the potential for life, would have profound implications for our understanding of life's origins and our future as a species. It would raise new questions about the uniqueness of our planet and the potential for life to exist elsewhere. Imagine the day we discover an exo-Earth with signs of life, like oxygen, methane, or even industrial pollutants. It would be one of the most significant discoveries in human history, fundamentally altering our view of the cosmos and our place within it. This is why missions like the HWO are so important. They bring us closer to answering the age-old question, are we alone? The Habitable Worlds Observatory is set to be a game-changer in the search for Earth-like exoplanets. By using direct imaging, it will give us the most detailed look yet at planets beyond our solar system, potentially revealing new worlds where life might exist. As we prepare for the launch of this incredible mission, the excitement is building. We stand on the brink of a new era. In conclusion, continued. The Habitable Worlds Observatory is set to be a game-changer in the search for Earth-like exoplanets. By using direct imaging, it will give us the most detailed look yet at planets beyond our solar system, potentially revealing new worlds where life might exist. As we prepare for the launch of this incredible mission, the excitement is building. We stand on the brink of a new era in exoplanet discovery, one that could answer some of the most profound questions we've ever asked. But this mission is just the beginning. The search for habitable worlds will continue to evolve as technology advances and new discoveries are made. The HWO will pave the way for future missions that might be able to not only detect, but also visit these distant worlds. Imagine sending a probe to an Exo-Earth, sampling its atmosphere, and even searching for signs of life. These are the possibilities that the HWO opens up. In the coming years and decades, as the HWO and other missions continue to search the skies, we may finally find the answer to whether we are alone in the universe. This quest is not just about finding other Earths. It's about understanding our place in the cosmos. Every new discovery brings us one step closer to understanding the universe and our role within it. The search for Earth-like exoplanets is a journey that will continue to inspire and challenge us for generations to come. As we look to the stars, let's keep asking questions, keep exploring, and keep dreaming. The universe is vast, and our journey is just beginning. So, keep doing science, keep looking up, and stay tuned as we continue to explore the universe and our place within it. Who knows? The next Earth-like planet could be discovered sooner than we think, and it might just change everything.